Okay, perfect. Hello, everyone. Thank you for coming. My name is Zander, aka captainGeech, and today I'm going to be speaking about a research project I did building a modular malware implant framework leveraging the V8 JavaScript engine. So today I'll be talking about some background and motivation for this research, briefly discussing the V8 JavaScript engine itself, and then I'll describe some of the features of the platform and do the open source release. So background on myself, I am a senior security engineer at the Google Threat Intelligence Group, which is a new organization formed as the merging of the old Mandiant Threat Intel Group and Google's Threat Analysis Group, TAG. I used to do cybercrime for a few years, and I'm recently switching to do exploit brokers and surveillance vendors. I know there have been some talks and research on that space, so if anyone wants to chat afterwards, definitely come find me. I don't do offense work as part of my day job. I've always been interested in it, but I am not a red teamer. So if I make some assumptions that are inaccurate or I miss something in the state of the art, please call me out on it. And I have some of these IDA stickers that I made if you want one. Okay, first, this is something I did in my personal capacity. This does not represent Google at all, and all the code and everything being released is my personal product. These are not Google. Don't tell Google I did any of this. So first of all, some background. So modular malware is not a new concept. It's been around for quite a long time. The implants themselves are typically fairly lightweight, and they just will execute modules being shipped down from the server. Some malware uses a bit of like a hybrid approach to this, like Cobalt Strike Beacon. The full implant has a lot of built-in capability, but you can execute compiled plugins to provide additional functionality. The benefit of modular malware is it gives you a lot more flexibility when you're operating in a target environment rather than having to have all the capabilities figured out beforehand and baked into the implant. So my motivation for this was I didn't think the current state of the art was all that sophisticated. The most common approach is to have pre-compiled modules that are specific to a target operating system and architecture, where if you have to have all the information ahead of time, then you have to go prepare the module, and it provides a lot of extra overhead to operators. Another interesting approach to this is from some research published by SentinelOne on a group called Sandman. They had an implant platform called Lua Dream that used the Lua scripting engine to provide a more flexible runtime environment for modules, but that requires writing Lua, and I'm not really a huge fan of that. And another interesting thing I saw is Cracked Spider's Havoc platform. He built a custom RISC-V-like virtual machine environment to run plugins, but I think this suffers from a lot of the same limitations as the Cobalt Strike and Beacon object file approach. And I know a lot of scripting language-based implants like Fin7's Griffin platform support evaling extra modules, but that's just like scripting language doing scripting language things. I didn't really consider that to be in scope here. So I wanted to build something that provided a lot of low-level performant code for network, C2 traffic, all the things that we don't want to worry about as module authors at a lower level with high performance, and then have a simple scripting environment that operators can use to build modules on the fly. Performance and stability are of course required, and I wanted to do something cross-platform and cross-architecture, and I also wanted to be able to debug modules on target. And so for this, I want to use the V8 JavaScript engine. So V8 is a super powerful open source JavaScript engine. It powers pretty much every single web browser except for Firefox, which uses its own JavaScript engine. Its powerful feature is that it can be embedded into other applications. So obviously the browsers themselves are embedders of V8, but Node.js is also an embedder of V8. The underlying JavaScript runtime for Node is V8. It is super capable. It exposes a lot of advanced functionality for embedders, including the ability to debug and profile code running in this system. And obviously, it has high security features because it's used in browser contexts. So code is all sandboxed and everything. And it's very difficult to run code in the JavaScript sandbox that will take out the system unless you deliberately enable that to happen. And so when you're embedding V8, there are a few core concepts of the V8 platform I just want to introduce. So when you're leveraging V8, there is a top-level platform that defines like where the internationalization resources and how should the platform be constructed, and all the feature objects in C++ are derived from the platform. And then from that platform, you can create multiple isolates. And isolate is essentially a distinct copy of a JavaScript VM. So it has its own managed heap and its own set of resources, and two isolates don't really talk to each other. And then within isolates, you can create contexts, and contexts can communicate with each other within the same JavaScript VM. This is kind of akin to share resources from different origins in the same tab. You can enable the security context for calls to happen across those origins, but you have to manually set that up, whereas two tabs don't really talk to each other. And then a handle is a smart pointer-like object in V8 land Essentially, it's a pointer to an object that's managed by the V8 heap and its garbage collector. So as things leave scope and everything, the V8 runtime under the hood will handle freeing those and doing garbage collection and all that fun stuff. So that's enough about V8. Now let's get into the platform. So I built a platform with a cross-platform C++ implant, obviously with the JavaScript runtime on top of it. The server side is all written in Python, so it's pretty easy to iterate upon. There's a simple command line interface for operators to use to manage and task modules. It is not super feature rich for reasons I will get into at the end of the talk, but it supports module packing and the ability to debug modules on target. So these are the commands that are available in the main operator interface. Quite simple. You can enumerate and reload modules on the fly, task the implant to run them, and then disconnect the implant. From a JavaScript runtime perspective, through embedding of V8, you can introduce custom objects into the runtime as global variables, kind of like how the window JavaScript variable in a browser points to like the current window. Those resources are all managed by the browser code itself, but they get exposed into the runtime. So I built a object that I was calling context, CTX, to expose a lot of OS-native, OS-agnostic functionality that would be useful for CNO module development in the runtime. So lots of features for raw memory manipulation, executing shell commands, interacting with the module output buffer, manipulating files, and I have a foreign function interface as well. I also was able to define different read-only constants in the JavaScript runtime from C++. So things like file modes, seek operations, memory permissions, those constants are defined once in C++, and those values just get copied into the runtime. So if you add new functionality, you can't really forget to fix the value on JavaScript because it's all the same value. So here's a simple example of an implant.js module. If we're running on Windows, we call the whoami command, and on Linux, we call ID. So here we've connected from Linux, and so we run the ID command, but then on Windows, we run the whoami command, and the output comes back to the server side. Module packing is a fairly naive implementation, but it would be doable to like replace it with like doing a proper webpack with source maps going down to the implant side. Here I'm essentially just merging JavaScript modules together. So this module is importing code from libutils, which has some constants being defined, and then the module is able to leverage those. The architecture of the client was very much focused on reducing the amount of work required to add support for new operating systems and architectures. So the JavaScript runtime interfaces with different native code for things like file I/O, memory manipulation, in the foreign function interface that handles all the hard work of managing state and tracking objects that need to be freed when the module finishes and things like that. And then those wrappers are then interfacing with the OS-specific code. So if you want to add, like, we have Linux and Windows right now. If I want to add Mac support, I would only have to rebuild that bottom layer and hook it into the rest of the runtime, and then automatically implant.js would support Mac OS modules. So as an example of this, walking through the call stack, in JavaScript, this is what I would need to do to allocate 500 bytes of heap memory. So we call that function. The V8 runtime then calls a callback that I've defined when I establish the runtime to allocate memory. And this parses the arguments coming in from the JavaScript runtime and then goes to the state object to request the allocation. In the state object, we determine what type of allocation actually needs to be performed. And then since we're doing a heap allocation, at this point, this is where the only OS-specific code has to be written. On Linux, we're using the glibc default heap via malloc, but on Windows, we're using the default process heap with a heap alloc to get that allocation. So all this pointer gets returned back up the call stack, managed by the state, will get freed when modules are finished being executed, and the JavaScript side now has a section of native dynamic memory that it can leverage for other operations, and it doesn't have to worry about like the V8 garbage collector trying to consume that memory or free it or overwrite it. It's in a totally separate context. So now let me show a demo of this. Okay, so this is a module where we have a couple different OS-specific features for Windows and Linux to try to check if we are root or admin, depending on what those terms mean on that specific system. So first, I will start the server. And then I'll run the Linux client first to connect to the server. Now I can run the recon module on the client, and we get the output, and it shows the proper output for how things are configured on Linux. So this is from low privilege context, so I don't have root, and I don't have any admin privileges on this user. Now I'll disconnect from the Linux implant, and then I'll head over to my Windows VM and connect the Windows implant. And then we can run that same module and get all the Windows specific behavior that we care about from the exact same code. So this shows the output like who am I/all, and then we see that we don't have system, but we do have admin, based on what those terms mean on Windows. So now let's talk about how module debugging works. So debugging embedded V8 is not super trivial, but once you build the underlying concepts, it's super easy to actually extend. So it has interfaces that it exposes to instrumentation and interrupt the execution of modules. Most of the time when benign embedders are leveraging this functionality, they essentially just proxy the traffic from the embedded V8 debugging over WebSocket to Chrome, because Chrome has a fully featured debugger as part of its developer tools, and you can tell that to communicate with a different service instead of the actual built-in code in Chrome that's executing. This communication happens over the Chrome DevTools protocol, which is effectively just JSON RPC, but with all the specific methods for debugging JavaScript code. So this is an example of a message being output from the V8 debugger, indicating that a script finished executing and the context was destroyed. There are a lot of different methods supported in the Chrome DevTools protocol. However, the vast majority of them are only supported in Chrome. For V8 embedders, there are only a few different namespaces of methods that are available. However, the two that we care about are debuggers and runtime. So all of these two domains provide all the functionality that we need to do basic debug operations, like setting breakpoints, enabling the runtime, looking at variable values, etc. Implementing the debugger requires two different objects to be implemented. I won't go in details on all of this, but essentially an inspector client is what gets called when the JavaScript runtime stops, and then the client needs to do something to send new commands, like set a breakpoint or continue execution. And then the inspector channel is what gets called from V8 as events happen. So if the debugger stops, if a new script is loaded, any sort of like callback event gets executed on the inspector channel. There's another function called the flush protocol notifications. Based on the name, I'm assuming this gets called when like it's done doing something and we need to ensure that all the messages have been written. But it's not documented at all, which is a big theme when you're working with V8. And nobody else embedding V8 really implements this. They all just kind of like put an empty function, including Samsung and Microsoft. So I figured if they don't care, I also don't care. So that is defined as an empty function. The command line interface is very similar to any other debugger you would use. The syntax is kind of a mix of WinDebug plus GDB. The terms I liked in both I kind of just like stole and put in here. So you can single step through execution, set breakpoints, all that fun stuff. You can list the source code, and you can evaluate arbitrary JavaScript expressions on the target side, similar to how the browser developer tools, the console, you can just like execute arbitrary JavaScript in that like REPL environment. This is that same type of thing, but happening over C2 with that being executed on target in the proper context. So as an example of how this works in practice, on the C2, let's say I want to set a breakpoint on line 5. The C2 server packages that up into its C2 protocol, sends that down to the implant, where the implant decodes that and identifies that it's a break set command being sent. It will then pass it on to the debug engine side, where it will make a JSON RPC call into the V8 inspector, calling the debugger.set breakpoint RPC method, which will provide like the line information, all the information required for the debug breakpoint to be registered. Then we can resume execution. At a certain point, V8 will hit that breakpoint. It will emit a debugger.paused event over the inspector channel, which then gets processed back on the implant netcode side into a context packet, which will tell the C2 server execution stopped. This is the line number. Did we have any exceptions? Did we error? Can we continue execution? Things like that. So this on the C2 server side, we see that execution stopped at line 5, and then it will print out the current context. And it's a good thing we stopped because I like my root file system. So here is a demo of the debugger at work. So here is a V2 version of the recall module I previously demoed, where we're now starting to look for SSH keys that we can steal. And so this code I wrote quickly and poorly, and it probably has a bug, so I'll run it on the implant and test it out and see if it works. And we're testing in prod like all good engineers do. Okay, so the server's running, the client gets connected to the server, and then we task it to execute that module just normally. And so we run the module, and an exception was thrown. That sucks. We probably need to figure out what's going on. So the implant is still connected, all gets gracefully handled. So we'll rerun that module in debug mode, so we can kind of inspect what's going on and try to figure this out. So I'll set a breakpoint on the line where the exception was thrown, and then resume execution. And so execution stopped, but no exception was thrown, which is great. So I can now inspect what the output of that function actually would look like. And oh, it's an array. So I need to update my code to actually take a string to put into the output buffer instead of just an array, which isn't currently supported. So I'll go back over to the module code and just take the first element of that array just for testing purposes. So then we can save the module and then reload the modules on the C2 server using the reload command. And then we can rerun that module on the target and see if that fixed our bugs. So there's still an exception, so my code is still garbage, but it's a different error, which means we made progress. So yeah. So technically progress, but the debugger did work and help us solve a bug. Okay, now let's talk about the foreign function interface in implant.js. So all this is great. We can interface with native code through the callbacks defined in the runtime, but there's always going to be functionality that an implementer wants to use that isn't already exposed, such as calling obscure 132 APIs to execute some specific functionality. To do this, there's a robust FFI interface that is fully typed. So the code top left is showing how you can resolve the enum device drivers API out of psapi.dll on Windows. The return type of this function is type bool, and it takes 3 arguments, a pointer, an integer, and another pointer. And so this function gets called, execution goes into the native code side, where it resolves that function through executing load library A to get a handle to that DLL, and then using getproc address to get the address of that. Instead of just returning that address into the JavaScript runtime, where it would be really easy to accidentally corrupt that and terminate execution through a memory segmentation violation. That pointer gets stored in the internal state of the implant, and a handle gets returned back into the JavaScript side. But the handle is wrapped in a function. So on JavaScript, you can just execute enum device drivers like you were calling a normal function, but under the hood, it gets translated into dynamically executing that native code from psapi.dll. Now, you might be asking yourself, why are we using enum device drivers in our JavaScript implant? I thought a good demo for showing the capabilities of a robust foreign function interface is to do kernel exploitation in JavaScript. And I did some digging. I'm unaware of any existing kernel LPE exploits written in JavaScript. So this might be the world's first for doing something really dumb in JavaScript. So this exploit that I wrote is essentially a port of an exploit written by a researcher at VMware. And it looks like my internet finally crapped out. So give me 1 second. I have this video locally as well. Oh no, my laptop died. That is super not cool. Okay, 1 moment. This is what I get for using Arch Linux. We're on time. Okay, I have time. I'm going to reboot my laptop. Give me 1 second. No, my laptop sucks, so I'm going to reboot. Does anyone have any questions on plain text support?
You were reloading the JavaScript. Was that sending it down from the server, or was that somehow editing it?
No, so that was reloading. So when the server first turns on, oh, it's still dead. When the server first gets started, it loads all the modules that exist on disk and packs them up. So it does all the module packing so it's all ready to go when you need to task the implant to execute something. the reload command essentially was triggering the server to reload all the modules off disk, repack them into memory, so that when you task the client to execute it, it's all ready to go. It just has to send the code down to the implant. Okay. Given this failure, I still recommend Arch Linux, just for the record.
What stack do you use for your network code, like to do your HTTPS and WebSocket?
It's just like a raw binary protocol. I wanted it to be super obvious on the wire and easy to detect. So it's just like a raw binary protocol, which is also the easiest to implement. I don't like using libraries in C++ because I'm lazy and I like PyPy and like crates on Cargo and Rust. C++ library management kind of sucks, so I didn't want to do that. Chrome, okay. That's going to be hard to do. Okay. Okay. Thank you for your patience. It will be worth it, hopefully. Okay, here we go. So this is the exploit. It is based, I essentially ported some work from a VMware researcher who exploited a vulnerable driver. So we're going to load up the implant on a system where I have the vulnerable driver running, and then the implant got connected, so we'll check the current permission levels. We see that we just have like a normal medium integrity context. Then I will run the kernel exploit, which uses arbitrary read and arbitrary write primitives from the driver to overwrite our current process token with the system process token. And we run whoami, and we see that we did indeed get an NT authority system shell. So this implant is now running as system, and all the JavaScript modules we execute will then have system permissions going forward. So we can all sorts of fun hijinkery on the system all over JavaScript with system context. So now let's talk about actually doing the public release of implant.js. So this is going to be a little harder when I can't see what I'm going to be presenting. But git commit again. Yay. Git push. Okay, implant.js has now been publicly released. Yay. So you can go to this GitHub repo. All the code is there with some information. I want to clarify a few things though. When people release like fully featured, weaponized capabilities publicly, and I see them used to deploy ransomware in a hospital, it really pisses me off, and I had zero desire to contribute to that while also presenting what I believe to be an improvement in the state of the art for modular implant development. So the code that I'm releasing is not capable, is not usable in an operation. What it does do is it provides a great research platform for other interested CNO developers to take this work and operationalize it on their own, in private hopefully, to build something cool and hopefully build on this work, which is licensed under the MIT open source license. So I'm only releasing a couple modules just to showcase the functionality, which will be the things I've demoed today. And there are no binary releases. The only condition where I will share binaries or IDB files is if you are a researcher with some reputation or someone I know, and you're having issues getting it to build because it's non-trivial to build, then I'm happy to work with you to improve like detections and things like that. So like I said, my goal is to enable researchers to benefit from this platform, but ensure that bad faith actors are not able to easily leverage it to commit harm against unwitting victims. To that end, I also have a lot of pre-made detections available. I work with the Proofpoint Emerging Threats team to develop a bunch of Suricata rules. So a massive shout out to Janina and Stuart at Proofpoint for their collab on this. The rules all got published yesterday, so ensure you have a recent version of the ET Open rule set or ET Pro, they're in there as well. And you'll detect a bunch of different facets of this on the wire. I'm working on some segment rules for host-based detections. Unfortunately, I didn't get those quite done yet, but I have some detection ideas and different behaviors in the repo documented. And I have several Yara signatures that also look for different facets of the Windows and Linux implants. Now, there's a lot of future work that I think would be valuable here. The FFI interface, while super capable currently, is quite difficult to use, especially with complex types. So first of all, keywords are kind of annoying in a scripting language where doubles are the default number type. So JavaScript does have big ints, which are arbitrary precision integers, but they're signed by default. So like doing like pointer operations with signed integers is just like kind of a bad day. So Theory has a platform called pwn.js, primarily supported for browser exploitation, but the underlying concepts are great for doing keywords and like large integers, so that could be nice. The binary is super big. Stripped on Linux, it's 70 megs. Before stripping, it's half a gig. The PDB alone for the Windows build is like a full gig. It took IDA an hour to load this thing. So getting this smaller would be great, and one interesting way to do this would be to dynamically load the V8 runtime from an existing Chrome installation, which every Windows computer has because Edge is just Chrome. A lot of Linux users will as well. So that could be interesting. I did not get a chance to do ARM64 builds. Mac OS recent systems are the obvious candidate for this. I try to be engine agnostic, but I'm sure it's slipped in on some places. Another interesting opportunity could be to do WASM-based plugins. The V8 runtime natively supports WASM, so having an interface to transpile plugin code from a scripting language into WASM could be valuable, and less strings equals a little harder to detect. And finally, on the topic of FFI improvements, structs are a little challenging to represent. Right now I'm just having a block of memory and just like offsetting into it. Working with some native C++ types to expose easy ways of doing memory manipulation for forming structs would be super valuable in improving the efficiency. And with that, thank you for coming to my talk. If you have any questions, feel free to reach out, and I have some IDA stickers. Thank you.